It has three main topics actually. Okay. So as our last topic, we're gonna now discuss mostly about sound waves. Okay. This is still a wave, still a mechanical wave, right? Sound wave is still a mechanical wave, mechanical longitudinal wave, but mostly, so we're going to talk about the properties of sound wave and some applications. So three major topics on our last lecture. So first, we're going to talk about the intensity of sound and loudness of sound in decibel scale. And then second topic will be Doppler effect, a very famous, Doppler's effect. And finally, sound wave interference, okay, the sound wave interference, the main concept of sound wave interference will be again used in your optics class. Okay, so that's our last topic. So these are the topics. So we're going to talk about sound wave, pressure wave, sound intensity, decibel level, loudness, Doppler effect, and sound wave interference. So these are the topic actually on this lecture slide. So first of all, sound and light waves are everywhere, right? These are the basis of hearing and seeing, right? Sound wave and light waves. Without them, you can't do anything. Sound wave is longitudinal wave, right? Unlike the transverse wave, the particles of the medium vibrate parallel to the direction of the propagation of wave, just like this, right? So when the speaker vibrates, what's going to happen? It creates this compressed and rarefied region, okay, in front of you. So this is the speaker cone vibrating, right, producing music or some sound, right? So it creates a high pressure and low pressure zone around it, okay? So that's why sound wave is also called the pressure wave. Why? Because it creates a low pressure and high pressure region. That's why it is also called a pressure wave. Just like this. See, here the air molecules are compressed, right? And here the air molecules are rarefied. So pressure is below atmospheric pressure. Here pressure is above atmospheric pressure. If you draw the pressure versus the distance, then you will see the pressure fluctuation like this. So sound wave is a pressure wave. And you can easily convert sound energy, sound wave into the electrical signal, electrical wave. What you need is, you just need a microphone, right? And source of sound. And you can just connect it with the interface to the computer. And then you can easily convert, the sound energy into electrical energy easily in the lab. So here, one more basic thing. So sound wave is a pressure wave because why? Because when the speaker vibrates, it creates this pressurized region, high pressure region, which propagates, right, over distance. That's how sound wave is propagated. So since the air molecules are compressed in this region, this must be a high pressure region. But it goes actually, the pressure amplitude, right, and the displacement amplitude, right, are opposite phase, the phase difference between the pressure wave and the displacement wave have a phase difference of 90 degrees. Why? Because at a point where pressure is maximum, displacement must be 0 and vice versa, right? And let me show you this animation. I have already shown you this animation when we did the standing wave in pipes. So let me try to explain this. So you have this waves in a pipe, standing wave in a pipe, right? This is a closed and open end pipe, right? So let's see what happened here at the closed end. What do you do? So closed end is the position of node because particles can't vibrate, right? So if you now plot, this is the displacement amplitude, okay, right? This is the position of node, and this is the position of antinode. This is called the displacement versus position diagram. This is the actual displacement in amplitude. But if you plot in pressure, in case of pressure, it will be opposite, see? Because pressure in this region is compressed. So this position in contact with the tube, closed end of the tube, must be at higher pressure, right? Because the air is compressed, right? So if you go to displacement plot, it will be opposite, see? So our conclusion is pressure antinode is displacement node and vice versa, right? Because of their nature. So any question on that? Any question on this?
So they're inversely proportional with one another?
they have a phase difference of 90 degree. You can say that, yeah. They have a phase shift of, in terms of plot, in terms of plot, they have a phase shift of 90 degree, because when the pressure is maximum, say here at the node, right, at here, the displacement is 0. That means it's basically a sine or cosine curve. So if you consider pressure as a cosine function, the displacement curve will be a sine function. So that means they have a phase difference of pi over 2, 90 degree phase shift. So that's the thing you have to understand first. So you may want to try this applet. But unfortunately, this applet works only with Internet Explorer. Okay, it may not work with the Chrome browser. Even with the Internet Explorer, you have to copy the address to the security, Java security manually if you want to play. Okay, so next is sound wave spectrum. Okay, so human ear or brain can detect sound frequency in the range of 20 hertz to 20 kilohertz. That's our range. That's the audible range, right? That human brain can detect, right? So below 20 hertz, we cannot hear. And about 20 kilohertz or 20,000 hertz, again, we cannot hear. This is the sound wave spectrum, right? Our spectrum. But different animals have different capacity, as you can see here, right? So you can see elephant, and actually it's not on the list. The elephant and this blue whale, right? Whales can detect actually well below 5 hertz, very low frequency. They communicate with very low frequency, very powerful and very low frequency sound actually. That's how they communicate. And they can travel actually tens of kilometers, sometimes hundreds of kilometers, okay, through water. That sound is called infrasonic. So infrasonic is below 20 hertz, and about 20 kilohertz is called ultrasonic. So that's the name actually came from ultrasonic. Ultrasonic means ultrasonic wave, which means it's higher than 20 kilohertz. And they have different applications, right? The ultrasonic wave, which is a very high frequency sound wave, can be used to image some tissues, interior body organs like this, right? Because they have very good resolution, because resolution will increase by the frequency. Whereas the low frequency sound can be used for sonar navigation, because they can travel very far distance. Whereas the high frequency sound can be used for imaging purpose, or this bad uses ultrasonic waves actually for for radar purpose. They use actually high frequency ultrasonic sound wave, right, for detecting its prey. Okay, so many applications, just like I said. So this sonar navigation uses low frequency sound, and these are high frequency sound. And this radar, something called radar gun, also use ultrasound wave to measure the speed of your car. Okay, so they have different applications. So next is bits. So what is bits? So first, let me show you an example, and then I will explain some mathematical concepts on bits. So bits is actually, if you sound, two frequencies, source of sound, similar frequencies like 500 hertz and 505 hertz, let's say. If you sound two frequencies, source of sound, pretty close to each other, like 500 and 505 hertz together, you will hear a ringing sound. Okay, you will hear some ringing sound, and that phenomenon is called bits. So, and what's the cause of bits? I'm going to explain both mathematically, So, and bit frequency. So let me first show you this applet. So about what is bits. So bits is the ringing sound produced as a resultant wave when two source of sound, similar frequencies, similar frequencies are sounded together. So I'm going to sound 500 hertz and 502 hertz, right, together. So if you take two tuning fork, one has 500 hertz, the other one has 502 hertz. If you sound them together, So if you guys can hear, right, you will hear something like this ringing frequency, ringing sound. Okay, now let's increase slowly. Let's increase the frequency of the second source a little bit. See, the beat frequency, it's called beat frequency. The beat frequency increases, and exactly mathematically, the beat frequency is just the difference, the absolute value difference between two sources, two frequencies. That's called bits, basically. Okay, and you can play with that. If you just differ by just 1 hertz, let's see, right? So it's a 1 hertz bits. You'll hear 1 bit in 1 second, right? Because the difference in frequency is just 1 hertz. So this is the bit frequency, okay? And if you now differ by 10 hertz, see, the frequency has increased. The beat frequency is exactly 10 hertz, right? Okay, so what's the main reason behind that? Let's talk about that. So main reason behind that is easy, actually. It's because of the interference of sound waves, that's it. Okay, you have two vibrations, their frequencies are slightly different. And if you sound them together, they will interfere constructively or destructively over time, okay? And that's the main reason of producing beats. So this animation will clearly explain that. See, you have two frequencies, right, sounded together, having slightly different frequencies, right? And over time, what will happen? As a function of time, right, sometimes they will meet in constructively, right? It's called in phase, right? We know this is constructive interference, right? See, they meet in phase, peak to peak, trough to trough. But at some time they meet opposite phase, see? Peak meets with trough and so on. They produce no sound. So you'll hear this ringing sound, loud and no sound, depending on the frequency difference. This phenomenon is called bits, okay? And how do you calculate the beat frequency? So you can now this is just a simple harmonic oscillator, right? You can just consider two tuning fork, right, as two simple harmonic oscillator, and then using the trigonometric relations that we use in the very beginning, you just combine these two, and then if you combine these two, you will end up with this equation, okay? These two equations, and then let me briefly explain this equation and how to calculate the beat frequency. So let me explain this mathematics. I will just I'm not going to take too much time on this because we have to do other stuff. Okay, so now beat frequency calculation. So you need a trigonometric relations, right? Because you're basically adding the sine functions or cosine functions, right? So let's take two sound waves. So since it is sound wave, we're gonna just say S1 is the first source of sound, and its wave function is what? We're gonna just call SM. SM is the sound. Since it's sound, you could just replace by A, amplitude. So I'm just gonna call S of M. That means the maximum displacement of sound wave. It's the sound wave amplitude, right? And cos or sine, so we're going to take cos. So omega 1t, right? What is S2? S2, so we're going to take, these are identical waves, right? The same amplitude, cos, but slightly different frequency, right? So if now you have two sources of sound, right? Having slightly different frequencies are not same here, but amplitude are same. Now, what would be the resultant? So resultant wave will be just the superposition of these two, right? From superposition principle. So then your SM cos omega 1t plus cos omega 2t, right? And then now to add this, you're gonna need the trigonometric relations, right? And you can go back and see in the wave topic. So this is cos u plus cos v, right? Or cos theta 1 plus cos theta 2. So if you add them from the trigonometric relation, you're going to get 2 cos u plus v divided by 2, okay, times cos u minus v divided by 2. That's what you get from trigonometric relation. So you have 2 times s of m, 2 times the amplitude, and then you have this cos omega 1 plus omega 2, right, divided by 2. That's the common factor, right? Times cos, same thing, omega 1 minus omega 2 divided by 2 times t. And we're going to call this is the average frequency. We're going to call this just omega. And this omega 1 minus omega 2, let's denote by omega prime. Okay, just some for shortcut, you know. So then we're going to get 2s of m. So we're going to put this here, cos omega prime t, right? And cos omega t. So this is now a new amplitude, right? Amplitude of the resultant wave. But this amplitude depends on time. It's a new time dependence. Time dependent amplitude. Okay, so that's what you get, where omega prime is omega 1 minus omega 2 divided by 2, and omega we have substituted what? Omega 1 plus omega 2 divided by 2. Okay, now if you plot this wave, see this is what? This is a new amplitude, time dependent, right? Depends on time, right? And so you can clearly see, since omega 1 is what? Pretty close to omega 2, because to hear the beats, the frequency of this sounds must be pretty close actually, right? Otherwise you won't hear the beat actually, you can't detect. So since they are almost equal, then you can say omega is much, much bigger than omega prime, right? Because omega prime is omega 1 minus omega 2 divided by 2, while omega is just addition, right? So that's why you can clearly see that omega is. So then if you plot this, you'll hear this. This is, if you plot that, right, in computer, so you'll get this, you have slow varying envelope, right? And it continues like this. This is basically bits. Okay, this is the bit. This is the resulting wave. And that's we simply call, that's the reason you hear ringing sound. Right? And we saw that mathematically as well, right? Because you'll get a new frequency, this frequency, right? Almost equal to the original frequencies, right? Average frequency, you can say average frequency with a new amplitude. And this amplitude is a slow varying amplitude, right? It's a slow varying amplitude. It's like an amplitude modulation. It's called amplitude modulation AM signal in electronics, right? You get this slow variation in this whole envelope, you know. That's what you get if you plot that. And that's simply called bits. So what's the bit frequency then? What's the cos variation is +1 to -1, right? The maximum and minimum values of cos is what? +1 to -1, -1 to +1. So for whole cycle, one full cycle, right? For one full cycle, the cos will vary from what? Maximum to minimum of +1 to, if you plot the cos, right? Like this, right? For the whole cycle. So if you plot the cos function, the full cycle, right? It starts from 0. 0 has maximum cos, right? Like this, right? So, and the maximum value is +1, -1, right? So for this full cycle, in one cycle, you have the maximum occurs twice, right? In its cos cycle. In a whole cycle, cos has 2 maxima, +1 This is also maximum. This is also maximum. So the beat frequency has to be 2 times this, right? So the beat frequency, omega, we call omega, and we will change into plane frequency, has to be 2 times this, omega 1 minus omega 2, 2 times that one, because cos, the maximum cos occurs 2 times in one cycle. So, but omega prime is omega 1 minus omega 2 divided by 2, and that, and omega is 2 pi frequency beat, is in terms of linear, right? 2 pi f1 minus 2 pi f2. And finally, the beat frequency is basically f1 minus f2, just the absolute value, right? So just the difference between two frequency is the beat frequency that you will hear, that ringing sound. Okay, so we saw mathematically, right, the beat, we have proved the beat frequency is just the difference between two frequencies. All right.
Could you go back up a little bit?
Yep.
So up a little bit more. So where it says S equals 2 SM cosine, that part,
yep.
The part with the squiggly, is that the new amplitude?
Yeah, this is the new amplitude, yep.
That whole thing is the new amplitude.
This whole thing, I call it new amplitude, yep.
Okay. And
so
then
new amplitude, right? Cos omega t, something like that. It's a new amplitude, this whole thing, a new amplitude. It's a time dependent.
New time dependent amplitude.
Yep. Time dependent amplitude, because the amplitude say depends on time, right?
Yeah.
Because cos, the value of cos goes from positive value to negative, and it depends on time. So that's what we see, because this is a time axis, right? In this result, this is a time axis, time versus y, right? And see, its amplitude depends on time. But the frequency of the original sound, right? This frequency of the actual sound is much, much greater than the frequency of this envelope, right? All right, so that's about bits. That's all you need to know. You don't need to know more about bits. And we can easily produce bits in a lab, actually. You just need a tuning fork having similar frequencies, 500 and 504 hertz. And if you just, vibrate two tuning forks, you will clearly hear this bit frequency. Okay. Now, that's our formula. Now, our main topic.
So, Professor, one more thing I was curious about.
Yep.
So when you say that this is all we need to know about beats, does that mean the only thing we really need to worry about then is the frequency of them?
So the only thing you need to know is this formula. And so how you got this this envelope, just physically, just conceptually. So if you superpose these two sound waves having slightly different frequency, what is the cause of this variation? That's what you need to understand. That's basically, it's called bits. And we just explained that from this mathematical relation. And the only formula we have in bits is this. For all the numerical calculations, this is the only formula you need. Okay, any other question? And this is the animation for the same thing. Okay, next is now intensity of sound. And how do we measure it in real life? So intensity of sound, right? Just like intensity of light, right? Intensity of sound is defined as power flow per unit area, unit surface area, right? If you have a speaker or source of sound, right? So at some distance R, right? How do you measure the intensity of sound? So by definition, sound intensity is defined as the power of this, let's say this is source is a speaker, let's say 10 watt, 100 watt, whatever, right? So power of that source divided by the surface area, because sound waves, right, travels in a three-dimensional sphere, and that sphere grows bigger and bigger. That's how sound wave travels, right? So this power flow, right, power divided by the surface area of the sphere is we define as the intensity of sound, okay? And its unit is watts per meter square, as obvious, right? And since it is a sphere, sound grows as a sphere, spherical wave. So it has to be the surface area, 4 pi, and surface area formula is 1, or 4 pi r square, right? Where r is the distance from the source to the given point where you want to measure the intensity, okay? And it can be shown that, so we will just say, it can be shown that the intensity of sound is proportional to the square of the amplitude, okay? The intensity of sound, right, at given point is proportional to the square of the amplitude, not just the amplitude, square of the amplitude. It can be shown, right, but you need some higher mathematics for that. But we will just use that term. Intensity of sound is proportional to the square of the amplitude. Okay. So that's the intensity of sound, just a plain. But measuring intensity like this, you know, is not very helpful in real life. And I will explain why, okay? So in real life, the auditory sensation in human is proportional to the logarithmic of the sound intensity, okay? So what does it mean? So that simply means here, so I will just try to explain. So if one person is singing, let's say the loudness, we will hear the loudness, right? Loudness is, let's say 1. So if 10 people are singing, then loudness will just increase by 1. So loudness becomes 2. And 100 people sing, right? Then loudness becomes 3. That's how we perceive. That's how the auditory sensation in human work actually. It's basically our ear or our brain cannot distinguish between 1 watt or 1.1 watt, let's say, in that way, right? Our brain basically cannot detect 10 watt and 12 watts of sound intensity at given point, at given distance. We cannot detect that, right? Just like a earthquake Richter scale. It goes logarithmic scale. So you feel some change every time you know the power increases by 10 times, something like that. That's called log scale, right? So the measuring intensity like this in a plain way, you know, this formula is not very helpful in real life. Because why? Because you cannot distinguish between 1 watt and 1.2 watts. Okay, our human ear cannot detect that. So we need a different scale, and that's called log scale. How do you measure? And this is called the loudness. Okay, loudness is the intensity our brain can hear is called loudness. Okay, and it just we will put this loudness formula like this. Loudness is beta. Loudness is defined as, is symbolized as beta, right? And just the ratio of this, the ratio of the intensity of the given sound from the given source, and you compare that intensity with some minimum intensity that human ear can detect, and take the log, 10 base log, and multiply by 10. Why? Because the unit is in decibel, not in bales, in decibel, because 1 bale has 10 decibel. That's why you have to multiply by 10. And that's called loudness. This beta is simply called loudness. And that's the thing we hear actually. We can detect, we can distinguish. Okay, so what is I naught here? So I naught is called the threshold of hearing. Okay, I naught is the threshold of hearing. That's the minimum intensity that our human ear can detect. That's what we call threshold of intensity. And we know that exactly, we know that number. It's a very low intensity. It's 10 to the power negative 12 watts per meter square. Okay, so that's the formula for measuring the loudness of sound in real life. So you first get the intensity, actual intensity, right? And divide it by the threshold of hearing and take the log of that, right? And then multiply by 10. And because we want to measure in decibels. And that's called beta. The standard symbol, most of the book use actually is beta. Beta means the loudness. That means the sound intensity that human ear can distinguish. So, and here's how it changes. See here, if you double the power or double the intensity, right? What will happen? That's just 3 decibel increase. If you double the power, right, or double the intensity, the decibel loudness will only increase by 3 decibel. Okay. So now if you increase the power, right, by 10 times, let's say intensity by 10 times, then the decibel will increase by 10 decibel. Okay. See, every time it increases by, every time the power increases by power of sound, intensity of sound increases by 10 times, then you will feel some you will feel some difference between the sound level. So that's why we need this scale in log scale. Okay. And here,
what are decibels?
decibel is the unit of loudness. The unit of this whole thing is decibel. Okay. It's just like bells, you know, one bell has how much intensity. That's how it is. It was originated, you know. It's bells and decibels. Okay. So this is the unit where, this is the sound loudness, you know, intensity that human ear can detect, distinguish. And it goes like this, you know. And here's some examples of, so we measure the sound in decibel in real life, okay? Not in watts per meter square. Because, why? Because you can really distinguish. So here are some examples of the decibel sound level, you know. Sound level is measured in decibel, right? Or is also called loudness. Of some example, so here, so threshold of hearing, right? Threshold of hearing has 0 decibel. Why? Because you're comparing this with the same intensity, 10 to the power negative 12, right? So 0 decibel means that's the threshold of hearing for human, but different animals have different capacity. But for human, 0 decibel means that's the threshold of hearing in decibel scale. And let's see, so threshold of pain is 120 decibel, right? Threshold of pain is 120. So so your ear needs some ear protection, ear plug actually. If you have a sound loudness, you know, after 90 or 100 decibels, it's a really loud noise. So the aircraft engine, jet engine produce about 140 decibels, okay, of decibels, just to compare. See here. So our ordinary conversation produces about 65 decibels, okay. So quiet automobile produce about 50 decibel, okay. So something, and so on, something like that. So sound level, you know, is measured in this scale, not in this scale. These are the related associated sound intensity. Any question?
Yes, I was wondering if you go back to that slide relating.
This one?
Yeah. Yeah. Can you explain the way in which power and.
So the x-axis is the ratio of the power. You're comparing 2 powers actually. You're comparing 2 speakers. So here's the one, right? Same power. And you double the power here. You triple the power here. You 5 times power here. 10 times power here, right? You just, and then how much decibel will increase if you increase the power, you know, like this. You're just comparing with 2. And it can show, clearly it doesn't go linearly, right? It goes logarithmically.
Quick question then. Say we were trying to measure like how loud it is, whatever. Would you first take the noise around you in decibels and then have that as power 1 and then your new sound as power 2 and then get the, I guess, change in sound for that is what decibels measures? Like that ratio?
Okay, so let me explain the same graph. So let's see here. If you double the power, right? If you twice the power level between 2 speakers, right? So how much will the decibel increase if you double the power? Let's see that. Let's see this particular example, right? And so loudness or decibel level. Explanation. So you have said two powers. So P2 is, should double the, you have two speakers, right? Let's say you double the power for the second. So how much, so what would be the decibel increase, right? For the second speaker. So let's calculate that. So we have, our main formula is beta is what? 10 log I over I naught, right? So power is, remember, intensity of sound is power over area, surface area, 4 pi r square. But if power goes double, intensity also goes double, right? If power becomes double, intensity also goes double. Okay, so now you just need to find out two beta, two loudness. So one is 10 log I over I naught. I naught is a constant. It's a threshold of hearing, right, for human being, which is this. That's a standard number, right? So beta 2 is what? So 10 log twice I, because you double the power, right? Double the power means double the intensity. But question is, by how much the loudness will increase? Loudness will not be doubled. Definitely we know that, right? But by how much? Let's see. So then you just take the difference between these two. So beta 2 minus beta 1, right? So it's 10 is common. Log twice I naught, right? Minus log I over I naught. And then just use some log properties after that. So 10, so the log x minus log y is what? Log x over y, right? I guess. Log x minus log y is, yeah. Okay, so then you use this property here, log twice I over I naught divided by this whole thing, I over I naught, right? But this is constant. So this is also log 2, 10 log of 2. And log of 2, if you do the calculator, right? If you use but make sure you use the 10 base log, not the natural log. These are calibrated with 10 base log. So log of 2 gives you 0.301, right? It's about 3 decibel change, see? So that's what it is showing it. And you can do the 10 times, you can do whatever you want, right? So that simply means, even if you double the power, right? Even if you double the power, the sound level or loudness will not get double, okay? It will just increase by 3 decibel, right? That's the meaning of that curve. Any question? So that's what it is. See here, double is right here, right? If you double the power, because it's a P2 over P1 ratio. So power gets double, the decibel level will increase by only 3 decibel, plus 3 decibel. Okay, so these are, and some, what is 0 decibel mean? 0 decibel doesn't mean it's, there's no sound power, okay? 0 decibel simply means it's the threshold of hearing for human being, right? Just for human being. That's the lower scale for human being. But many animals have different capacity. They can, so this, for example, this harvest mouse shown here, right? It can hear very quiet noise as low as negative 10 decibel, right? Or even cat actually. Cat can hear much below than 0 decibel sound, right? And so on. Different animals have different capacity. So this is the one I just showed you, right? This is the one I just showed you. And now let's do some problems now. I'm gonna solve some problems, and before I assign you something. Okay, so when you solve problem, then so we will revisit all these formulas, and then it will be more clear. So I'm gonna now go back and try to solve as many problems as possible. Let's see. Sound waves, okay. So let's do some problems. Okay. on decibels, sound loudness, right? Okay, so here's the first problem. There are many problems that I just randomly collected some problems. So here's the first question. It says, first question is, right, how many decibel is hundredths of I naught? What is I naught? I naught is the threshold of hearing for human being, right, for us. And what's that value? Is 10 to the power negative 12 watts per meter square. So it's asking, what's the decibel level for this? So you're now I is I naught divided by 100. That means it's 100 times less than our threshold of hearing, right? But some animals can hear that even that, we cannot hear that, right? But some animals can hear that. For example, cat, many cats can hear that sound actually. And what's the decibel level comparison, right? Loudness, right? That's what we measure the sound. So now just use straightforward formula. So 10 log I over I naught, that's the formula we have, right? Decibel level formula. And just put that I as 100 over 10. I naught over 10, that's it. So 10 log, this is I naught divided by 100, right? And in the you have 100. So I naught will cancel out. It's basically 10 log 1 over 100. And just do that calculation, right? That's the decibel level of this sound. So log of 1 over 100 is 1. So just use the calculator. Make sure you use 10 base log. It's negative 10. So 10 times, this will give you negative 2, right? And this is negative 20. What's the unit? Decibel. So cat can hear actually as low as negative 20 decibel. We can hear only 0 decibel, minimum sound level. But cats can hear actually negative 20 decibel, very quiet sound. Right. So this is just a straightforward one, right? Any question? Okay, next. This is the next problem. So next one is this. Loudspeaker produces a sound level of 120 decibel at some distance, right? Distance is not given. What would be the loudness if there were 20 such identical speakers at the same distance, right? So here's the question. You have one speaker, right? Just one single speaker, right? And at some distance, we don't know the distance. You have, let's say initial, let's say beta 1, right? What's the what's the loudness in decibel scale produced by single speaker is 120 decibel. Now it says, if you have 20 such speaker, similar, identical. If you have 20 identical speaker, right, 20 of them, right, at the same distance, what is the new decibel? That's the question. At the same distance, right? Same distance. Same distance R. What's the new decibel, right? So definitely it will not be 20 times this, because the loudness will not increase linearly, as we know, right? Definitely it won't be 20 times. But how do you find that? Just use the similar concept that I just showed you actually in the beginning. So you did, so first of all, if intensity will be, however, our plain intensity, if one speaker produces I, right, at some distance, due to 20, it will be 20 I, right? Because it does increase linearly. Our intensity does increase, intensity or power does increase linearly. If you have 20 speaker, the intensity will be 20 times I, but not this loudness that we hear. Okay, now just use the same formula. So beta 1 is 10 log I over I naught, right? And beta 2 is 10 log. Now power has increased by 20, so 20 I over I naught. I naught is the threshold of hearing. So you just need now beta 2 minus beta 1. Just take the difference, right? And find beta 2. Beta 1 is given. So again, 10. So I'm going to do shortcut. So 10 log 20 I over I naught divided using the log property, you know, I over I naught. So this will cancel out. Basically 10 log 20. So beta 2 is basically, beta 1 is 120 decibel is given, right? Plus 10 log 20. And that's gonna give you, so first of all, what is log 20? Log 20 is 1.3 and times 10 is, this is 13 decibel. So only 13 decibel increased plus one. So answer is 133 decibel will be the new sound level. So the decibel increase is only 13 decibel, right? Even if you increase the power by 20 times, right? The loudness will only increase by 13 decibel, right? Because it increases logarithmically. So that's the question. Okay. Any question?
Yeah. So why do you have to do beta 2 minus beta 1? Why can't you just solve for beta 2?
So how do you solve for beta 2 directly? Do you know the distance?
No.
Yeah, so if you know the distance, you could solve beta 2 directly by finding the power from here. First, find the power, right? The speaker power. And if you know the distance, then you can directly use this formula, right, to find the beta 2. But in this problem, the distance is not given, so you cannot do that.
If the distance were given, how would you find that exactly?
Yeah, so if the distance is given, then you can do either this way, right, shortcut, or if the distance is not given, if the distance is given, then first you can find the power, right, the power wattage, right, of this speaker. Because why? Because you are given the decibel, right? So if suppose the same problem, right? Suppose the distance, let's put distance as 1 meter, let's say, just for example, right? If the distance is given, say, some distance, let's see. Okay, let's put some distance as 1 meter just for simplicity, right? Then you can solve the beta 2 directly without those equations, because first find the power, right? Because beta 1 is actually 10 log I over I naught. And then beta is 120, 10, right? Log I over, this is 10 to the power negative 12, right? That's threshold of hearing. And then this is 12 is log. So let's put I as I right now. And so first let's solve the intensity. And then once you find the intensity, since you know the distance, you can find the power. First of all, the log property, how would you get rid of the log? Because to solve the I, right, you have to get rid of this I, log. How do you get rid of this log? What's the log property?
Put it to the 10 to the power of that.
Yep, that's so it's called taking anti-log both sides, right? 10 to the power 12. Whatever you get, it becomes 10 to the power 12. Is now you're left with this. This is the log property in math. Okay, so your I is just what? This is 1 watts per meter square, right? And then, but I is what? Power divided by 4 pi r square. And then you can solve for power. Power is just 4 pi r square, right? 4 pi. R is 1 meter for simplicity, right? Just 4 pi, right? Put the actual watts. This is in watts. So once you find the power, then you can find the beta easily, beta 2. Because power of the speaker doesn't change, right? Now for beta 2, you have your I2 is what? I2 is 20 times speed because you have 20 similar speaker and 20 times 4 pi. That's your new power from 20 speakers. And then just do this, follow the same equation, 10 log I2, and you have to compare with the threshold of hearing. So 10 log I2 is this, 24 pi, right? Divided by 10 to the power negative 12. That's it. And you will see, so find that out. Okay. Any question? Okay, now you can do the same similar, right? So if the intensity of sound is increased by a factor of 5, right? The decibel reading of an instrument measuring the sound will increase by how many decibel? Basically, you're doing the same, exactly same. So you have beta 1 is some decibel, right? So it's basically asking the difference between two sound level. When you increase the sound by 5 times, increase the intensity. So it's basically asking beta 2 minus beta 1. So what is beta? Beta 1 is 10 log I over I naught. What is beta 2? Beta 2 now 10 log, you increase the intensity by 5 times. So 5I by I naught. And just take the difference, do some log algebra, right? And find that out. It's basically same, right? So these are all similar. So let's do one more.
Just for a second.
Which one?
To number 3.
This one?
Yeah, I'm good. Thank you.
Yeah, so number 4, number 5, similar. So let me do one more. A rock band playing an outdoor concert produces a sound at 120 decibel, right? The rock concert usually produce actually that much sound level. That's the actual number actually. Rock band produces just like a jet engine actually, a single jet engine. 120 decibel sound is very intense sound actually. At what distance? Now you are given the distance, 5-meter distance away from their single working loudspeaker. What is the sound intensity level, however, at 35 meters away? So here's the thing. Now you have only single speaker, right? And it says at R1 is how much distance? 5-meter distance, right? This is the observation point. Your loudness is 120 decibel at 5-meter distance. Now it's actually, the speaker is the same, right? Now at further distance, 35 meters away, what's the loudness? Clearly loudness will decrease, we know. So now your distance is 35 meters now, right? What would be the new loudness? So that's the question. So then you just do the same thing that I just showed you. So first find the power, right? And power will not change, right? Because you use the same speaker. The speaker power will not change. So from this first data, since distance is given, first you find the power, right? So beta 1 is 10 log I over I naught. So this is 120 decibel, 10 log I over I naught, right? So again, it's 10 to the power 12, right? Is I over I naught is 10 to the power negative 12. So I is just 1 again, 1 watts per meter square. Then you can find the power of the speaker because I is what? I is power divided by 4 pi R square, R1 square, right? This is I1. So power is now 4 pi R1 square because I1 is just 1. So find that out. This is the speaker power. 4 pi. So R is 5 meters initially, right? So the power is 314 watts. That is constant, right? The power of the speaker doesn't change. Now it's asking what's the loudness at 35 meter distance. Now you have to calculate beta 2, right? To find the beta 2, first you need I2, the new intensity, right? Is power will remain same, but distance is different, so R2 squared. So it's 314 divided by 4 pi 35 square, right? So I2 is now 314 divided by 4 pi, right? But distance is 35 now. Okay, now it's going to be, the intensity will be 0.0204, right? Watts per meter square. Now, what is the new loudness? So new loudness will be now back to same formula, 10 log new intensity divided by threshold is 10 log I2 is 0.0204 divided by 10 to the power negative 12. And your beta 2 is, what is the 0.02, so log, 10 base log 0.0204 divided by 10 to the power negative 12. Okay, so that's gonna give me 10.3. 10.3 times 10 is 103 decibel, right? Remember, beta 1 was 120 decibel, and that was at 5 meter distance, right? Obviously, it will be intense, right? Loudness will be intense actually at low distance. So at 5 meter, it was 120 decibel, but if you go farther away, 35 meter distance away, the loudness has decreased by 17 decibel. All right, guys, any question?